carbon dioxide monitoring, mainly about capnography. So those who haven't, I hope those who didn't join the class on gas analyzer watched the tutorial or read about it. So this is not a continuation, but during that topic we skipped capnography, but we have talked about the broad principle of gas monitoring, including carbon dioxide. So this is just continuation. So in today's class, we will talk about carbon dioxide analysis, the various methods, just recap, and then a recap on what is IR absorption spectroscopy. Then we go into specifically on carbon dioxide monitoring. Okay. So what is the term meant by collision broadening? And in IR absorption spectroscopy for carbon dioxide analyzer, we have two types, mainstream and sidestream. We have to know the differences. Then the terms definition of capnogram, capnograph, capnometry. Then we will look at the normal waveform of a capnograph and causes or conditions when an abnormal wave graph will appear and how does it look like, the morphology. Then the important part is end tidal CO2. Please mute. And tidal CO2 variation, the causes of it. Then finally, we'll talk about the differences between alveolar CO2, arterial, and tidal CO2. Before going to topic, just to re-emphasize, for primary, the top 3 equipment that you have to know in and out is pulse oximetry, invasive arterial line blood pressure, and capnography. Okay. So not only in MCQ and SAQ, it is a very famous question in Viva. If you make it to Viva, sure one of these will come out. Okay, so you have to know in and out. So this is our core recipe. We'll come into this picture multiple times today, the capnogram. Okay, the waveform, the morphology, how is it look like in a pathology and everything. Okay, recap. We talked about gas analysis, breathing circuit, and blood sample. Breathing circuit for oxygen, nitrous oxide, volatile gases is mostly a percentage. For carbon dioxide is partial pressure, millimeter mercury. Where, please mute. For blood sample, it's content for oxygen and carbon dioxide and pH measurement. We have talked about it. So in breathing circuit, the distinguishing feature for carbon dioxide, it appears in millimeter mercury. The only gas that appears in millimeter mercury is carbon dioxide. Everything else in a percentage. So whereas in blood gas, of course, we get all the oxygen and carbon dioxide in millimeter mercury. So we have talked about it. Tomorrow, we're going to concentrate on the carbon dioxide. Okay, we know there are 5 different various type of analyzer: Raman scattering, mass spectrometry, IR spectroscopy, photoacoustic, and gas chromatography. What is important here is the IR spectroscopy. That is the most commonly employed carbon dioxide analyzer in our GA machines and ventilators. Whereas for chemical measurement and blood sample is Severinghausen electrode. So what today's topic on capnography will be going in depth about IR spectroscopy. So again, the IR spectroscopy wavelength for carbon dioxide is 4.3 micrometer. And this wavelength will be absorbed. The fractional concentration of the carbon dioxide will be measured and converted into partial pressure. Okay, we have talked about Dalton's law. And Dalton's law say partial pressure of individual gases summed up together equivalent to a total pressure. So how do you want to find out the partial pressure of each gas? Is fractional concentration of that gas times with the total pressure, you will get the partial pressure. So facts about IR absorption. First, infrared light, the frequency is below the red light. That's why it's called infrared. It is not visible to human naked eye, lower frequency than visible light. That's why you have a pulse oximetry. You can only see the red light. You don't see the infrared light because it's not visible to naked eye. It is absorbed by gases that have 2 or more at different atoms, like oxygen. It does not absorb infrared because OO, same atom. So we can see oxygen, same atom, it does not absorb. Infrared just penetrate through without any absorption by the oxygen molecule. Whereas gases that have a different atom, like carbon dioxide, nitrous, and volatile gases, they will absorb. There is infrared light being emitted, will absorb. The non-absorbed light will pass through the gases and reach the detector. Okay. Then this is a simplified diagram of infrared absorption spectroscopy that should be able to write, you're able to draw. You can just put a circle here to say it's an infrared source. Then you must draw the two. This is a sampling chamber. At the two end, you must mention there is crystal sapphire window, the importance of it. We don't put a glass here because glass will partially absorb infrared. So whereas the crystal sapphire window does not absorb any wavelength. So all the infrared wavelength which is emitted from the source will go into the sampling chamber. The sample goes in, sample goes out. In our topic today will be carbon dioxide, but IR spectroscopy can be a multi-gas analyzer for volatile nitrous oxide as well. So absorption of the wavelength by the gas molecule, the wavelength that is not being absorbed will reach the detector, will be processed by the microprocessor, and will be displayed as the waveform and the numerical measurement of the EtCO2. The infrared gas spectroscopy can be a single multi-gas. It works by the Beer's law, not the Lambert's law, because Lambert's law only for pulse oximetry, where our vessel diameter can be bigger and smaller according to vessel constriction or vessel dilatation. Whereas in GA machine, the sampling chamber size, the diameter of it is constant. So Lambert's law does not come into play. Only the Beer's law. It means the concentration of the gas molecule. More the concentration of gas molecule, more wavelength get absorbed, less reaches the detector. So fraction of radiation absorbed by gas mixture will be determined as the concentration or partial pressure of that specific gas. So only Beer's law is being employed in carbon dioxide measurement here, whereas in pulse oximetry we have Beer's and Lambert law both. So again, source, less gas molecule, less being absorbed, more reaches the detector. More gas molecule, more infrared being absorbed, less reaches the detector. The more that gas being absorbed, less reaches the detector, shows more gas molecule present, so higher fractional concentration of the CO2. So, and it will be displayed in the Capnogram. This all just recap. So this is what happens in our GA. There is a sensor between applied either at the mainstream or side stream. We'll come into that, and your gas molecule pass through in the CO2 breathing tube. The gas infrared light will be emitted onto the gas molecule in the chamber, then detected by infrared. The CO2 analyzer, the accuracy is plus minus 0.1% of carbon dioxide concentration up to 10% differences in EtCO2. So you have to know this. 0.1% of the carbon dioxide concentration up to 10% differences in millimeter mercury of EtCO2. Okay, that is the accuracy level. And for the wavelength per se, we have talked about different gases have different absorption wavelength. For volatile is 3.3, for nitrous is 3.9, and carbon dioxide is 4.3. So nitrous, some books mention 4.5 as well, but generally most of our recommended textbook mention 3.9. What is important here anyway, either 3.9 or 4.5, nitrous is the closest to the carbon dioxide. That is the important point here we need to remember. Either be it 4.5 or 3.9, it is the closest absorption spectra to the carbon dioxide. So that brings us to this. Why this is important? I'm talking about this nitrous oxide wavelength with carbon dioxide. That brought us to a term called collision broadening. When you talk about capnography, CO2 measurement, either in Viva or SAQ, you cannot run away from this term. It can come out in the SAQ 1 mark. Define collision broadening with example. So what is collision broadening? Gas absorb infrared waves maximally at certain wavelengths. Okay, each of them have a specific wavelength where maximal absorption of the IR wavelength occurs. For volatile 3.3, nitrous 3.9, carbon dioxide 4.3. Okay, this picture. Then if sample as pure CO2, let's say in our breathing tube. Okay, let's say in an ideal situation, the sampling chamber or the gas mixture only have CO2. There is no nitrous, there is no oxygen, there is no volatile. Okay, only absorption will occur at 4.3 micrometer for the CO2 molecule. Narrow band of absorption wavelength, IR is maximally absorbed like this. If the sample only have carbon dioxide, so the peak will be only at 4.3 micrometer because there is no other interaction with other gas molecule. So the band of absorption will be narrow and tall. Okay, IR is maximally absorbed. But in reality, we have gas mixtures in our breathing tube. Our patient usually have air plus oxygen mixture and also carbon dioxide plus if you're using gas inhalation anesthesia, of course inhalation is there. Okay, even though if you are doing TIVA, you are giving oxygen plus air and carbon dioxide is being exhaled from the patient. So it's never our gas mixture in our breathing tube, never pure carbon dioxide. So the in gas mixture, the absorption band get altered, broadened due to kinetic interaction, which is collision. Different gas molecule hit each other, they collide each other. So that is why it is called collision. And this collision causes collision broadening. They causes this absorption band get altered like this. If you look at it, it is occurs mostly with nitrous oxide because close absorption wavelength with the carbon dioxide 3.9 versus 4.3, or you take it 4.5 also, no problem. So you can see here it is CO2 plus nitrous oxide. Okay, when there is nitrous oxide, this absorption band compared to which is tall and narrow and tall, it become broadened. So thus it affects the accuracy of the absorption, the concentration measurement of the carbon dioxide. So this is collision broadening. The effect is it affects the accuracy. Just hold on. I just want to make sure did I record it? Just somebody give me a reminder. Yeah, okay, it's being recorded. Cool. Okay, so we talk about that. So this is in exam, if you ask to define for 1 marks, you just have to mention this. This is enough. These two sentences are in gas mixture, absorption band get altered due to kinetic energy. In infrared absorption software, mostly with CO2, and mention these values. Enough, you will get 1 mark. Okay, you don't have to draw these also. If you draw, it's well and good. If you don't draw, also never mind. Usually the 1 mark question. That brings us to, so now we know carbon dioxide is measured by infrared analyzer. Okay, so these infrared analyzer, based on where they are positioned in your circuit, okay, that will determine it is a side stream or mainstream analyzer. It's mainly based on the position of the analyzer in your circuit. So if you have a mainstream analyzer, the what important thing you have to remember, it is immediately near to your ETT. Okay, it is immediately near to your ETT. So this is your ETT, this is your analyzer. So this is mainstream analyzer. It is in the main circuit. That's why it's called mainstream analyzer. Okay, the analyzer is placed in the main circuit. It is connected immediately near to, as near as possible to the ETT. And then so the exhale gas from the patient will go through the sampling chamber in the analyzer, and the measurement will be displayed directly in the monitor. Okay, so this is your mainstream. Whereas in side stream monitor, which is most commonly employed in nowadays in our OTs and everything, where the sampling tube is connected to the HME. We usually, our ETT is connected to the HME, and usually we will connect our sampling tube, the CO2 sampling tube, the tubing, which is go and connected to our monitor, big monitor, where there as the analyzer. So when there is an analyzer is placed away from the ETT, it is called side stream. Okay, so the CO2 that is exhaled from the patient, it has to go through a sampling tube to reach the analyzer, which is placed away from the ETT circuit. It's away from the circuit. So you can see this is your ETT, exhale CO2 come from here. This is your sampling adapter, or we call it our, usually nowadays we don't place a separate sampling adapter, we'll just connect it to the HME. So it goes through the sampling tube and reaches the sensor and get displayed. That is side stream. Okay, mainstream attached to the ETT directly. Side stream in an intubated patient versus non-intubated patient. Mainstream only can be used in an intubated patient because it's directly attached to ETT, where side stream can be used in intubated or non-intubated patient. In an intubated patient, as I mentioned, it direct to the circuit, as in you have an adapter or HME, there is a sampling tube which connect to the analyzer. Whereas in side stream, in a non-intubated patient, the most important easy example is your nasal prong. When you give sedation for a patient, you put in a different nasal prong, special nasal prong with the Capno measurement. Okay, we will go into that. And also, if you have NIV, also you can connect the side stream CO2 analyzer to that in ICU and HDU and everything. We do that in a patient, especially in a patient with OSA and everything. We do that. So mainstream analyzer, just again for just to make a better understanding. So exhale CO2 comes from here. Then your infrared source of light will get emitted. This is a sampling chamber. It goes through the sampling chamber after pass through the sapphire window. Then it will get detected and then Capno will be immediately visualized. Okay. If you look at it here, CO2 goes from here. Look at the animation. Then you get your immediate result. CO2 from the patient immediately connected to the ETT, the analyzer, then goes out like that. So this is the photos that I just want to show for better understanding. So you can see this is your direct connection to your ETT. One side is connected to the ETT, one side is connected to the Y-piece and goes to the immediate direct measurement. We have the one that connected like this. Another one you have seen mostly in ICU like this. This is the adapter and you will put on a clip-on type of CO2 analyzer, which either in some ICUs and HDU or in district, I have this portable one. We have used this where it shows your ETCO2 and waveform here, or it is connected like this and it's connected to the main monitor where your ETCO2 and Capno comes out there. Okay, this is your Capnograph. You can see this one end can be connected to the patient end and another one to the circuit, whereas this is a clip-on IR source and detector. This is the adapter. So this goes into this adapter. Okay. So mainstream can be either a direct one or clip-on. Okay. Whereas side stream, again, side stream CO2 is being exhaled. It goes through the circuit as usual, but there is a sampling tube which is interconnected here, which will bring the CO2 away from heat and goes through the analyzer in the main monitor and you get your Capno. Okay, if you look at it, CO2 from the ETT goes from the sampling adapter, the tube goes in far away from the monitor, then only you get the Capno. Okay, by looking at this itself, you can somehow come out with the few advantages and disadvantages of this without even be discussing it. Okay, so side stream analyzer, if you look at it, so this is your side stream analyzer. If you use the NIV, you can connect to this one end to the mask, another end to your circuit. So you can see if it's a ETT, you can side stream, you can connect this and then there's a sampling tube goes in here. So this is, if it's connected to the HME, this is what I mentioned. This is your ETT, this is your circuit, the HME, then you have your sampling tube. So the sampling tube will go and connected to this one. You can find it in your ventilator. You can see a small one. Sometimes it doesn't read. The nurses will go and take it out and put a newer one. Okay, because it's been long and the thing. So the sampling tube sometimes also get water vapor block kinked. Have to change the sampling tube as well. So this is in an intubated patient. In a non-intubated patient, we can use the same one like this. As I said, can use in Ventimask, NIV and everything. Or where we have this, you see in ICU, some of the ICUs we have this ETCO2 sensor. They have, if a patient have asthma, patient everything, we say, can you please tell the nurses to connect the Capno? They will bring this and connect, and they'll bring the sampling tube and connect to the ETT. Or in a patient who have nasal prong also, we have a special nasal prong. We have that special nasal prong allows one side oxygen to go in, another side for carbon dioxide to come in. It is something called Salter eyes, SALTER, Salter eye. So this is the nasal prong, specially to monitor CO2. So now we have compared. This is the famous question. When you talk about capnography CO2 measurement, your question will start off with maybe a definition of a capnogram or capnograph, or define collision broadening, or list the various types of CO2 analyzer. Then they might, if the question want to ask about IR absorption spectra, draw a simplified diagram of IR absorption spectroscopy for CO2. And next, classify carbon dioxide analyzer. You have to define side stream and mainstream. And sure, the question will come out, compare and contrast the mainstream versus side stream CO2 analyzer. So there are many ways you can do it. The easiest way should be, one is in the design, and then based on the design, what is the advantages versus disadvantages. So as I mentioned, looking at it, side stream is small size, where mainstream is heavy and bulky. Because it's attached to the ETT directly, it causes, it puts a burden on the ETT and the circuit, heavy and bulky. So the airway weight get increased. Sampling tubing, you need a sampling tubing for a side stream, so it is long, so it might affect the accuracy because it takes, and the response time might be delayed because it's not direct measurement. Then response delay, of course, because of this. Humidity vulnerability, yes. Neonatal ease, for side stream, no, only can be mainstream, and such. I will share this slide later. I'm not going to go into it. My homework for you all is, you're going to sit and write a concise version of advantages versus disadvantages based on you're going to compare and contrast the features, and then we're going to compare and contrast the advantages. So I will share this slide later. The important one, you're looking at it like calibration gas required for Sidestream, yes. For mainstream, no. Use for non-intubated patient, Sidestream is yes, mainstream, no. So it can be advantages and disadvantages. So this is in Matthew O. It come out in one of the SAQ few years ago. All this again I will share. But what I find the simplest and shortest, that minimum info you have to write is this, short and sweet. Okay. This does not as the design. You can add on the design of it. Mainstream, it is in the main circuit attached to ETT. Sidestream, the analyzer is placed away from the ETT like that. You can write. Then you can mention the presence of sampling tube, whatever. But this information shows the advantages and disadvantages. The one that I'm saying about where is it placed and everything, design, this is advantages and disadvantages. The one that highlighted are the advantages. The one this side, the one non-highlighted are the disadvantages. Okay, this is the simplest and the minimal info that you must write to get at least, if there is a 5-mark question, you're easily getting 3.5 or 4.5. I'm just going to add on one more, which is calibration. Okay, sorry for the typo here. Calibration, which is mainstream not required, Sidestream is required. So this is a disadvantage for the Sidestream, is an advantage for the mainstream. So I will share this as well later. Okay, then we're coming into capnography per se. So how do we draw a simple capnogram and label it properly? Okay, your capnogram as an x-axis, which is the time, we'll come to it, which is time, and y-axis, which is the CO2. So before we go into the waveform and the different phases, we're going to talk about the terms. Here, a lot of books and sources mention phase 0, 1, 2, 3, 4. There's a lot of confusion. Some may start with 0, some may start with 1. So 0, 1, 2, 3, 1, 2, 3, 4, 0. So what I do, I will usually during my time, I just label it A, B, C, D, E, which does not confuse. Okay. It is less confusing, and for me, it is better to easy to remember rather than reading different notes and everything saying different phase, because the part that you want to understand is what phase is this in your inspiratory versus expiratory cycle. So A and B is your inspiratory baseline, B and C is your expiratory upstroke, C and D is expiratory plateau or alveolar plateau, D and E is your end tidal concentration, and D and E is your inspiratory downstroke. We'll come into it. Before that, we go into the terms. Capno stands for smoke in Greek word. So that's how the term capno, everything, capnometry, capnography, everything come. It's gonna measure smoke. So CO2 is taken as smoke. So we have 4 different things that you might ask to define, except from collision broadening just now. Can be capnometry versus capnogram versus capnography. The final one is end tidal CO2. So what is capnometry? Capnometry is numeric measurement of carbon dioxide content. Okay, there is no waveform. It is just giving you a value. Okay, this analyzer is only giving you a value. This meter is called capnometer. It sometimes can be qualitative. This is quantitative. It can be qualitative, where it can be so this is quantitative. When it's qualitative, it can be colorimetric capnometry, where this is the one. So this is a portable capnometer, which doesn't give any number, but there'll be a color change based on a chemical reaction upon exhalation of CO2. We'll discuss this shortly. So the device used is called capnometer. It can be a colorimetric capnometer, or it can be a numeric capnometer. So what we get is capnometry. It can be a quantitative capnometry, use a number, or it can be a qualitative capnometry. Next, we call capnogram. Gram means there is picture. So it is the same thing, not only the measurement. Here you get the waveform. So usually it's not, we'll never get a waveform alone. If there is, what capnogram means is only talk about the waveform without the numbers. So it's a waveform, CO2 concentration waveform over time. When it's combined with the numerical measurement, capnogram combined with capnometry, you will get capnography, where you have a waveform representation plus with the numerical value of the concentration. Capnometry accompanied by graphic display, which is capnogram insertion or waveform over time. So this is capnography. Okay, and the device we use is Capnograph. This is what used in our GA machine, the one that we talked about, the mainstream analyzer or sidestream analyzer. All these are Capnograph. So this is Capnograph. So you see, you have a measurement in a numerical and you have a graphical representation of your capnogram waveform as well. Okay, this is a portable one. It is used in for patient who are intubated, going for transport, everything, we can use this. We connect one end to the ETT, another end to the circuit. So it will directly measure and give you. Okay. So capnometry, capnogram, which is overlap when you have two, is your capnography. Finally, it brings us to a EtCO2. EtCO2 is the CO2 present in the airway at the end of expiration at here. We will discuss in detail about end-tidal CO2. Okay. So these are all definition that might be asked in your exam for 0.5 mark. Differentiate capnometry versus capnogram. So you have to mention these few words. Okay. So this is one slide on colorimetric capnometer. I don't think many of you not seen it. During my early days in MO, that when I was in HKL, we have given this. So when you go into intubate patient in wards and everything, so you want to know whether your ETT is placed properly or not. Have you intubated? It's not esophageal intubation. You have an endotracheal intubation. So you will, after intubation, you will just connect this colorimetric capnometer to see the color change to confirm. Then you connect to the ventilator. So this is but it can easily spoil, but I don't think no hospital uses this now. So what the color change is, it is usually in a purple or red color. Upon CO2 CO2 contact from the after we intubate patient, the ETT connect, the CO2 being exhaled, the color will change. Turn yellow when CO2 is detected. So purple when CO2 is very low, let's say your esophageal intubation, it will be still purple. 10 means CO2 around 4 to 15 millimeter mercury. CO2 more than 15 millimeter mercury means your ETT is 100% into the trachea and it will become yellow. So it's a pH sensitive chemical indicator, changes color on exposure to CO2. It's like a litmus paper. Okay, it's a concept is similar to a litmus paper. It's a chemical reaction upon to contact with CO2. So next, capnography in detail. So this is the picture that I'm going to use in my presentation. I'm not going to use other capnogram or other thing with the phase 1, 2, 3 and everything. So I'm going to stick to this A, B, C, D, E phases. You may draw it in your way. You're going to put phase 1, 2, 3. In your SAQ, you can do that as long as you label it correctly. You won't get penalized for 1, 2, 3, 4 or 0, 1, 2, 3. Doesn't matter. Okay. So the Y axis is your partial pressure of expired CO2. Okay, partial pressure of expired CO2, exhaled CO2, and your x-axis is time in seconds. Okay. So if you look at it, ignore these numbers. I'm not going to, I'm just want to show the value. So what is important here is your capnogram is divided into two phases, the inhalation phases and expiration phases. The earlier part of capnogram is from your airway dead space. When you exhale, the upper part, whatever that gas mixture is in your trachea and above comes out first. So that is your airway dead space. The second is mixture of airway dead space plus the alveolar air. And number 3 will be 100% alveolar air. So this part, the plateau part is your inspiratory baseline followed by your expiratory upstroke, then alveolar plateau or expiratory plateau, finally your inspiratory downstroke. So if you look at it, so this part of it, it's all about this area, this dead space, this airway dead space, nothing to do with alveolar. We talked about dead space anatomical versus physiological. So this will be your anatomical dead space, which is plus your equipment dead space. We are not only talking about airway, we are talking about anatomical, which is airway plus equipment. So these are the dead space, which is not including your alveolar. So when initial part of breathing is all about this. Okay. Then once we reaches the upstroke and the plateau, it's all about alveolar dead space. So this is your, then we go into your, if you look at it, this is your alveolar tidal volume. This is your airway dead space. then the end of your exhalation before it drops, that is your end tidal CO2. And then we have your partial pressure of arterial CO2, which is the final concentration, which we'll be measuring for your EtCO2 gap. We'll come into that later. So first, A and B, first phase, A and B. There are people who start from D and E. I will just go A to B. You won't get penalized. It's according to your understanding. So A and B is called inspiratory baseline. So A and B. So inspired air, we know ideally got no carbon dioxide. Okay. So the initial part during inspiration, baseline should be 0 in inspiration. Atmospheric air only got very low carbon dioxide, 0.3% only. So we have taken as inspired air, and in your fresh gas flow, when you give your fresh gas flow in your circuit, we give fresh gas flow of oxygen. Okay, and air which contain insignificant amount of carbon dioxide, which we are taking it, there is no rebreathing. Your soda lime is okay, patient is not rebreathing CO2. So your inspiration will be baseline 0. It's a flat line. Okay. Elevated baseline. Let's say this baseline is not 0, is elevated, mean patient is rebreathing carbon dioxide. Mean there is a lot of carbon dioxide going back into the patient. Supposedly, in the inspiratory limb of your circuit, there shouldn't be any carbon dioxide. If it's going, it could be malfunction in ventilator circuit, incompetent valve for the expiratory valve, or it exhausted carbon dioxide absorption circle system, exhausted soda lime, or low fresh gas flow. You are using an ultra low gas flow where it is not enough to circulate or recycle the CO2. So this will cause elevated baseline. You can see this is your baseline getting elevated. Sometimes you can see your EtCO2 is 44. The IN CO2, IN will be a small IN CO2. Inspired CO2 is also 4 or 5. That shows patient is rebreathing CO2. You must ask your GNS to change the soda lime immediately. Okay. So next, we talk about B and C. B and C as a early part and a later part. So this is expiratory upstroke. This is the beginning of exhalation. Patient is started to exhale, expire. So exhalation of CO2 free gas from anatomical dead space. As I mentioned, you have your anatomical dead space and equipment dead space, supposedly free of carbon dioxide. From your carbon dioxide from your blood comes in your venous circulation, goes into your right atrium, goes into your right ventricle, via pulmonary artery, it goes into your pulmonary circulation. These are CO2 rich blood. Then it get gas exchange in your alveoli. So alveoli to pulmonary capillaries, we know carbon dioxide is very highly soluble gas. So it will immediately gas exchange within blood to alveoli will reach equilibrium. So the CO2 at the beginning of your exhalation, CO2 are rich in carbon dioxide. So these are the phase that initially the gas that comes out from your airway, which is bronchus, everything have limited carbon dioxide. So that's why it's a flat line followed by a slow upstroke. Then the moment it goes into your alveolar, gas is coming out, they are CO2 rich. That's why there is a sudden upstroke. Okay, a lot of CO2 being exhaled, eliminated. So exhalation of CO2 free gas from anatomical dead space, which is central conducting airways and or equipment dead space. Your airway, your trachea plus your ETT, all these have low CO2. That's why the flat line. Later on, rapid upswing on the curve, which is due to mixing of dead space gas with CO2 rich alveolar gas, this part, B and C. Okay, I hope this is clear. So trachea and dead space initially have low CO2, this part. Later on, your alveolar, which is very high CO2. This is dead space alveolar. This is the CO2 alveoli that has gone through proper gas exchange. They are rich in CO2, so they will just shoot up. Okay, this is what happened at this expiratory upstroke. So the expiratory upstroke can have pathology in condition delaying delivery of CO2 from lungs to detector. So your analyzer is in the ETT, is in mainstream or side stream. If there is anything causing delay in delivering the alveolar rich CO2 to reach the sensor, it will cause this expiratory upstroke, this B and C, to have a pathology. So if it takes longer time to reach, then this will fall down. It will slant. So it will slant, the alpha angle get bigger. So it could be mechanical causes, King ETT, slow side stream sampling rate, or pathological cases where you have bronchospasm. The airway is being constricted. Or it could be either airway, it could be either your equipment. When there is an obstruction to this, either in the airway or the ETT, the CO2 is not reaching the sensor as soon as possible. Thus, there is a delay. So thus this B and C part of it will slant down. So that's what we see in patient with bronchospasm and everything. Next, we have a C and D, which is the expiratory or also called alveolar plateau level. It represents the CO2 rich gas from alveoli. Once the CO2 rich gas is coming up here, this is the part. Plateau means still this expiration is still going on.
Sorry, Dr. Karma, we can't hear you.
Can you all, am I audible now?
Yeah, you're
Yes,
audible
okay.
now, boss.
Okay. Okay. Where did I go mute? Here? Should I restart from here or even earlier?
Yeah, and the King ETT.
King ETT. Okay. So I can skip this. I'll just go to the next slide. This part done?
Okay, boss.
Okay, cool. Sorry, I think some technical error. Okay, so next we talk about C and D. C and D is the expiratory alveolar plateau. As I mentioned, here is we know IE ratio for our ventilation is expiration is a longer phase compared to your inspiration. So this is your earlier part of expiration where there is a sudden surge of CO2s being eliminated, and this is the part plateau where we are giving more time for complete elimination of CO2. Okay, so your expiration is longer. This is the part that is being saying. So why is it not a straight line? We call it a plateau, but is it a proper plateau? Is it like a straight line? No, because ideally, if you take as an ideal situation, if all the ventilation perfusion are well matched in all lung region, the VQ, ventilation versus perfusion, is well matched, 100% ideal and proper in all lung region, then all the alveoli will have the same PCO2. Okay, the venous rich blood in a pulmonary capillaries reaches your alveoli. If all your alveoli are properly being ventilated and perfused, VQ is perfect, they all will absorb gas exchange and they will have a similar concentration of CO2. Thus, at the plateau area, it will be maintained straight line, perfect horizontal expiratory plateau. But in reality, there is heterogeneity of alveoli. We have a VQ mismatch even in a LT individual. The VQ is never 1, is 0.8. There is variable VQ ratio, which is affected by your position, your comorbid, and a lot of things. So there is variable PCO2 in alveoli that causes the slight upstroke, okay, of this alveoli. So what happens is, why there is an upstroke, not a downstroke or anything? Because sensors will first receive lower level of CO2 from areas with higher VQ ratio. If you look at your, remember this class on hypoxemia and everything, VQ mismatch, we know apex versus base. Apex have both lower ventilation and perfusion, but ventilation is better than perfusion. So VQ is higher here, VQ is lower here. So ventilation is high here, it means the perfusion is lower. Lower CO2 rich capillaries are bringing the CO2 to this apex area, where these alveoli have better ventilation. They have exchange, but they only exchange lower concentration of CO2 because the perfusion is lower, compared to your base, where more blood is going to the base of your lung, where they have higher concentration of CO2. So this earlier part is your higher VQ ratio area that reaches your sensor, and the last part is your final squeeze of your lung. Your lung expiration at the end, it's a final squeeze of your lung at the bases and the collapsed area where they are pushing out all the CO2, thus causes the slight upstroke, okay, of your expiratory plateau here. Subsequently, higher level of CO2 from areas with lower VQ ratio. So if you want to put it easier, earlier is from the apex area, later is from the base area. Apex is higher VQ, base is lower VQ area. Alveoli with lower VQ areas have longer time constant. This brings you a concept of time constant. Okay, lower VQ area, the alveoli at the base in this example will have longer time constant. It means they contain relatively more CO2. They have longer time to exchange, to absorb, to pick up more CO2 from the pulmonary capillary, contributes to the later part of the phase 3. Sorry, my mistake. So later part of this C and D. You can mention phase 3 also lah. This one I think I copied. That's why I mentioned it. So it's the later part of this C and D, slight upward slope of the plateau. So thus, the slope actually represents the ventilation perfusion status of the lung. Okay. If the ventilation perfusion status is better, it will come more straight. If it's worse, the VQ is worse, then it will go more higher and higher. Okay, we'll come into it later. So the EtCO2, the end of phase of C and D is your EtCO2. The end of expiration is end tidal. This is your tidal volume respiration, is your end tidal CO2. So end tidal CO2 is the PCO2 value at the end of this plateau, at the end of expiratory phase. It represents exhalation from the most poorly ventilated alveolar unit, which is the low VQ areas lah. The normal value we take it as the same as PCO2, which is 35 to 45 millimeter mercury. Ideally, it is not the same as your partial pressure of arterial CO2, but in health, the differences are very small. So we take it as 35 to 45 millimeter mercury. The differences between arterial versus end tidal versus alveolar CO2 we'll discuss soon. Next, from the moment the exhalation phase stop, next patient start inspiring. So inspiration, as I mentioned, inspiratory air does not contain oxygen, contain carbon dioxide. Thus, there is a rapid downstroke, rapid descent of the graph from high end tidal CO2 to baseline of 0 as long patient is not rebreathing. So descending limb makes an almost right angle turn and rapidly descend to baseline. This is begin of inhalation. Fresh gas free of CO2 is inhaled and CO2 concentration fall abruptly to 0. The E phase, then your inspiratory baseline. So this is the different phases of your capnogram and what actually happening, physiology. Okay, then we have to talk about this alpha and beta angle, the importance of it. So the alpha angle is the angle between B and C and D. From the expiratory upstroke to expiratory plateau, this is the angle, usually taken as 90 to 100 or 110 degrees. The importance of it, as I mentioned, if there is a delay of carbon dioxide reaching from the lung to the sensor, in case of any obstruction to the airway or the equipment, this alpha angle will become larger. It means the graph will slant. So the movement from like this straight, it will slant because it takes longer time. When it slant, the angle become bigger. The slope of CD is dependent on the VQ status of the lung. Alpha angle indirectly reflects the ventilation perfusion status of the lung. Okay, the moment it becomes slower because of the obstruction or anything, it will causes alpha angle to become bigger. Next, we have beta angle. Beta angle is between C and D and E. It is also 90 to 100 degrees. Angle becomes larger if rebreathing or mechanical obstruction. Again, if this patient have mechanical obstruction, the EtCO2 will be very high, and then so that will causes this angle to become higher. Or patient is rebreathing, so the baseline will be high, so this inspiratory limb will become a bit slanted. Because supposedly the inspiratory downstroke will reaches a baseline, but if patient is rebreathing, the baseline will be elevated up to here. So the inspiratory will like this, then the beta angle will become bigger. Okay, we'll see the pictures of abnormal capno soon. So this is a summary of it. This is mentioning page 1, 2, 3, 4, but this I just take the put in. I will share this later just to for example. So as I mentioned, the alpha angle, you see bronchospasm or VQ mismatch, any obstruction or VQ mismatch, whereas beta angle is rebreathing or mechanical obstruction. Okay, this is airway obstruction, this is mechanical obstruction, but you can mention both can cause us any delay, can cause us the widening of alpha or beta angle. That brings us to abnormal capno. So abnormal capno, so this is the normal capno. So abnormal capno, you must know in bronchospasm or asthma, it will cause a slanted and sharp appearance of capno. I will share these slides later, all these things, so you all can read on your own. So the important part you have to mention is the word that use a shark fin appearance. So shark fin appearance will widen the alpha angle, and this one will look as shark fin. This is mostly in your bronchospasm. Okay, a COPD alpha angle between 2 and 3, more than 90-degree bronchospasm or VQ mismatch. So shark fin is for your mostly for bronchospasm. In severe obstruction, moderate to severe obstruction, you will lose the plateau. There is no more plateau. So it will be obstructed. So the delay of CO2 is very slow to the sensor until it reaches end-tidal CO2. The expiratory phase is somewhat finished before actually reaching the plateau, and inspiratory phase starts. So that is about, this is about shark fin appearance. Then in hypoventilation, you know there's hypoventilation mean there's less elimination of CO2. So the EtCO2 will gradually go up. Okay, baseline will be same, but this end-tidal CO2 will go up. Hyperventilation, the end-tidal CO2 will come down. Okay, because more CO2 is being eliminated. Rebreathing, as I mentioned, your baseline will go up. Okay, your EtCO2 will go up because of the baseline goes up. The whole waveform is going up and up and up. Okay, it could be because of faulty expiratory valve, low fresh gas flow, partial rebreathing, insufficient expiratory time. If you put a patient on IE of 1 to 1 and respirator very high, the expiratory phase is very much delayed, very much shortened. So patient does not have enough time to eliminate CO2. So thus more rebreathing of CO2 can occur. This is important in beta angle will become wider. Then in for our ventilation, pleural cleft, it shows us when the patient has started breathing, because during this inspiration and expiration, there shouldn't be any disturbance. We know patient inspiration is a negative pressure. So this is when the expiratory plateau going on. If patient is taking a breath, there is a downfall. We know inspiration as low CO2. So this is rich in CO2. Suddenly patient inspired gas has no CO2. So the CO2 will drop. That is why the pleural cleft. Pleural cleft shows patient is trying to breathe, and the patient that inspired air as low CO2. So that will causes the drop in CO2. That is the pleural cleft. The depth of pleural cleft proportional to degree of muscle cleft. If more depth, more deep, it means patient is more awake. Patient is regaining for muscle relaxation, is being reversed. Okay. Next is cardiac arrest. We know there will be a low cardiac output because your carbon dioxide elimination, for that pulmonary circulation, your heart must pump. Your right ventricle must pump for the blood, carbon dioxide reach pulmonary artery blood to reach the pulmonary circulation. Then only. If heart is not pumping, there is no circulation, there is no EtCO2. So absence of EtCO2, after you eliminate your equipment problem, it can be in cardiac arrest as well. And return of spontaneous circulation, you can see the moment a patient enters circulation, there will be a EtCO2 goes up. So these are use of capno. Okay. So this is again another form. Sudden loss of waveform means it can be either patient is arrested or patient is ETT tube disconnected, dislodged, kinked or obstructed. Means the exhale CO2 is not reaching the sensor, or there is no exhalation at all. Patient is stopped breathing. So that is sudden loss of waveform. And another one is when you see this oscillation, it's called ripple effect. It can be because of cardiogenic patient who have very severe arrhythmia, which causes heart beating that transmitted into your lungs, can causes this ripple effect. Sometimes water vapor also can causes this ripple effect. Okay. So another one is your esophageal intubation. You intubate, initially there is a waveform, then it just goes off. That can be a esophageal intubation because initial 4 to 5 millimeter of mercury can be of a gastric hair. After that, there is no CO2 in your stomach, so it will go flat. So that brings us to the concept of EtCO2. So what is EtCO2? EtCO2 is partial pressure of carbon dioxide at end of the exhale breath. Okay, normal value 35 to 45 millimeter mercury, and assumed to be representative, okay, of alveolar CO2. Assumed to be, remember this with assumed to be representative of alveolar CO2, but in reality, it's lower than ideal alveolar CO2 because the CO2 free gas from alveolar dead space dilutes it. I will come into this with pictures later. So what is the importance of EtCO2? It is equivalent. Okay, it is equivalent to pulse oximetry because you want to know the blood content of CO2. We take an ABG, we get a PaO2 and PaCO2. But in monitoring non-invasive method for oxygenation, we do pulse oximetry SpO2. But for no ventilation, the elimination of CO2 is correct or not, that is where the EtCO2. So the EtCO2 is a surrogate for carbon dioxide elimination, which is equivalent monitor to pulse oximetry non-invasively. Okay. So the factors affecting EtCO2 you must know. It can come out in MCQ. So as carbon dioxide, it's a product of metabolism. Okay, it is eliminated by the respiratory system. For it to reach the respiratory system, the circulatory system must work. So whatever that affects, whatever that can be altering this carbon dioxide metabolism and the pathway and the elimination. Carbon dioxide is produced because of the metabolism. So whatever that causes alteration in production and metabolism of carbon dioxide and the pathway of carbon dioxide from the blood to the heart to the lungs to the sensor, or whatever that can cause increase in carbon dioxide iatrogenically, all that can cause differences in end-tidal carbon dioxide. So metabolism is pain, hyperthermia, shivering. All these increase metabolism, increase carbon dioxide production. Respiratory system, inadequate ventilation, patient is not breathing well, there is a delivery system problem, bronchospasm, or reduced respiratory rate and tidal volume because of sedation. All these can cause increase in tidal. Circulatory system, increased cardiac output means more blood is being transferred. Patient having higher cardiac output also can increase the EtCO2. Medication in bicarb. When you give bicarb to a patient who are intubated, patient who you administer bicarb but you does not adequately ventilate the patient, you can see because when you give bicarb, bicarb will combine with water, carbonic acid will dissociate, become H2O and carbon dioxide. So carbon dioxide concentration will go high. So that's why when we give bicarb administration, we must adequately ventilate the patient. So decrease EtCO2 is just opposite of it. This is one way of categorizing it. Another way of categorizing it is by decrease alveolar ventilation, increase CO2 production, increase inspired PCO2 that I mentioned. I will share this again. You all can learn. Another thing, don't forget, don't only look at the physiology, don't only look at the human, also look at the equipment. So equipment can be sampling error, inadequate tidal volume, water blocking the sample line, or air entrapment into the sampling line. So all these can be a risk of end-tidal CO2, or another one is exhaust soda lime also can be a reason. So exhaust soda lime, elevated baseline, elevated EtCO2. Next, we talk about PaCO2 versus EtCO2 gradient, which is also called as EtCO2 gap. This is an index of alveolar dead space. Bring us to this concept. If you look at Y and X axis, Y axis is partial pressure of carbon dioxide. The most upper part is your PaCO2, your EtCO2 is here. So there is a gap between the PaCO2 and EtCO2. This gap indicates how much is the alveolar dead space. Larger the gap, larger the alveolar dead space, it means patient have higher VQ mismatch. Okay. So this statement is important. Arterial CO2 is higher than alveolar CO2, higher than end-tidal CO2. Makes sense, right? Your arterial CO2, your pulmonary artery CO2, your blood that brings back carbon dioxide, very high in carbon dioxide. So when they go to alveolar, it get mixed, that it drops a bit. When EtCO2 is even more drop because of dilution by alveolar dead space. So you look at it, we talked about this during hypoxemia. This is a normal alveoli where your PaO2 alveolar oxygen is 100, your alveolar CO2 is 40. Your blood that comes in as PaCO2 of 45, but when they goes through this, they will equilibrate to 40 to 40. Okay, but if the patient have shunt, it means when the alveoli is being perfused but not being ventilated. Okay, perfused but not being ventilated, no ventilation. So eye-rich gas will go in here, but the PaCO2 is also high in, so it will equilibrate directly and 45 millimeter mercury, it does dilute. Whereas if there is a dead space, your dead space is being ventilated but no perfusion. So the alveoli in this region have a lower CO2. So when the gas from this alveoli goes and mix with this normal one, if you look at these two, these and these mix, this will dilute this PaCO2, thus the end tidal CO2 will be lower. But if these two are mixed, let's say the shunt is more. If these and these mix, 40 millimeter mercury goes in, but here got 45 millimeter mercury. So this will help in result in increase EtCO2. If the patient has more shunt, the EtCO2 will be higher. If the patient have lower shunt, the EtCO2 will be more dead space, the EtCO2 will be lower. So that's the difference between. So we look at it here. So PaCO2 versus arterial versus alveolar CO2 gradient, normal value is 2 to 3 millimeter mercury, these two. It's very small due to the shunt. Okay, unventilated regions, higher CO2, unventilated regions. So these are the unventilated region, no ventilated region, higher CO2. They mix and bring up the partial pressure of arterial CO2. Okay, that's why the partial pressure of arterial CO2 is higher than alveolar CO2. Okay, this part. So widening, this can widen, the PaCO2 versus alveolar CO2 can widen because of incomplete alveolar emptying, pure sampling or VQ abnormalities. Don't worry about this much. We are more concentrated about this and this. Okay, next. This and this, the relationship is PaCO2, alveolar CO2 is more than end tidal. EtCO2 supposedly assumed representative for alveolar CO2, but in reality is lower than ideal alveolar CO2 because CO2 free gas from alveolar dead space, this one, CO2 free gas from alveolar dead space dilutes this EtCO2. That's the EtCO2 is lower than alveolar CO2. We don't measure alveolar CO2, it's by alveolar gas equation. So this is just to show the relationship. Next, the important one is this, the PaCO2 EtCO2 gradient, where your PaCO2 is bigger, much bigger. So this much bigger than EtCO2, which is called EtCO2 gap. Okay, this in your waveform, this is your capnogram. The end tidal CO2 is here, your PaCO2 here. So PaCO2 is more than EtCO2 in health. The differences are very small, can be negligible. 0.5 to 0.8 kilopascal, which is 3.5 to 6 millimeter mercury. This part, this thing. Okay, that's the differences. Gradient is an index of alveolar dead space. Sorry, gradient is index of alveolar dead space. The typo here, alveolar dead space. The gap between these show us the range of alveolar dead space. Bigger the space, bigger the alveolar dead space. Why? This is again, as I mentioned, in a normal patient, when you have a CO2 rich blood comes in here, goes here, it get equilibrate and goes out. Okay, the gradient from here is small. Whereas when there is a dead space, when you go PaCO2 here, the dead space actually dilutes this EtCO2. So the EtCO2 comes down, but the PaCO2 is actually higher, still high. Okay, the blood CO2 has equilibrated with your alveolar CO2, but the alveolar CO2 does not equilibrate with your EtCO2 because the dead space alveoli, which have lower CO2, dilutes the EtCO2. Thus, the range, the value of EtCO2 become lower and PaCO2 is still higher. So the gradient become larger. Okay, more alveolar dead space volume, there is a VQ ratio is high, means there is a mismatch. Less perfused alveoli, less CO2 uptake, more CO2 free alveoli. Okay, less perfused means there is a dead space. Dead space means wasted ventilation, right? Ventilation is there, but less perfusion. Less CO2 uptake, more CO2 free alveoli mixed with better perfused, thus more CO2 alveoli lowers the AtCO2. thus increasing the gradient between PaCO2 and EtCO2. So higher the alveolar dead space, higher the EtCO2 gap. So look at it. This is the healthy lung. There is EtCO2, PaCO2 gap is low. In a sick lung, there is a wide gap. Okay, the gap between EtCO2 PaCO2 widens in sicker lung due to greater amounts of dead space ventilation. When a dead space ventilation means ventilation is good, perfusion is low, thus the VQ ratio is high. High VQ ratio is not good. VQ ratio low also not good. VQ ratio high also not good. Okay, higher VQ ratio point towards dead space ventilation. Lower VQ ratio go into shunt ventilation, shunt perfusion. Okay. So the raised EtCO2 graph, any causes that increases alveolar dead space, thus higher VQ ratio, non-perfused alveoli, ventilated but under-perfused. So which are the condition the alveoli being ventilated but not perfused? In hyperperfusion state, BP low, in shock, less blood flow to the pulmonary circulation. No perfusion at all in a patient with cardiac arrest or pulmonary embolism, total obstruction or total cessation of flow to the pulmonary circulation. Pulmonary capillary compression. The BP is okay. Patient is not arrested, but these vessels, pulmonary vessels, are very small. They can compress when your alveoli become bigger. When in emphysematous lung, there is air trapping. So alveoli getting distended and distended. So the pulmonary capillaries around the alveoli getting compressed. So reducing the perfusion. Or in a patient with positive pressure ventilation, is very high PEEP. You use very high PEEP. The pulmonary the alveoli are getting stretched, thus compressing the pulmonary capillaries. Like in ARDS, when we use very high PEEP, when you use very high PEEP, you have to worry about high VQ ratio, which is the VQ mismatch. Finally, don't forget the equipment. Capnograph calibration inaccuracy also can cause raised EtCO2. Final, we bring us to uses of capnography. It can be asked. We have talked about it. CO2 is a product of a metabolism and is being transported in blood, bound to hemoglobin and dissolved in plasma, and it comes to your heart. So your heart, from right heart pump via pulmonary artery, goes to your pulmonary circulation, and then from your pulmonary artery, it goes into your alveoli and getting eliminated. So shows in your capno. So whatever this pathway can be used as to a monitor. The CO2 can be used to monitor this whole pathway. So users, first is a respiratory monitor, adequacy of ventilation. If the EtCO2 high, PCO2 is high, we know patient is not getting adequate ventilation. The elimination of CO2 is not good. Next, for ETT placement, for us to confirm whether it's an endotracheal or else there's no esophageal, is it a correct placement or not, or the ETT is kinked, or the ETT is not positioned well, is it dislodged, all that can be shown. Weaning of muscle relaxant, we showed the capnocular cleft. Patient is being ventilated, suddenly there's a curar cleft, that shows us patient being waking up. Next, CVS monitor, it monitors the adequate perfusion, let's say in cardiac output. So monitor cardiac output, RS&P, good quality CPR, okay. It is being advocated for us to use portable capnography during CPR to show the efficacy of CPR, because you have to at least maintain 10 millimeter mercury of EtCO2 during CPR to show you have a good quality CPR. Okay, if when you're doing CPR, if the EtCO2 is not reaching 10 millimeter mercury, it means your CPR is not good quality. And it also shows return of spontaneous circulation. The moment your patient already have circulation, mean there is return of spontaneous circulation, there is circulation to the pulmonary system, you will have a sudden surge of EtCO2 to show that your CPR is successful, patient has revived. Then can be used as a metabolic monitor, where it's malignant hyperthermia, increased metabolism, increased CO2 production. You have a exponential increase of EtCO2. When you have bicarb administration, your EtCO2, PCO2 will go up because of bicarb combined with hydrogen ion, carbonic acid will dissociate into carbon dioxide and water, carbon dioxide level goes up. Hypothermia, less metabolism, less EtCO2, low metabolic state. Patient who are ill, low metabolism, low EtCO2. Then finally, equipment monitor, it can use to monitor your rebreathing system. So your breathing system, whether patient having low gas flow or soda lime exhaustion, your baseline will go up. Circuit disconnection, no capnogram at all. ETT obstruction, you will have a shark fin appearance, or patient having ETT mucus plug or ETT dislodgement, all that. ETT dislodgement, sudden ETT disconnection, sudden loss of capnogram. ETT obstruction will cause a slanting of the capnogram. So it has 4 monitor: respiratory monitor, CVS monitor, metabolic monitor. If you classify like this and give the example, you will get full mark. Okay, so this is your connection to your ETT system, which is commonly used for Sidestream analyzer to show you all. Okay. Okay, summary, I will share this again. You have to know the waveform in detail, including the phases, alpha and beta angle, what's happening. Then you have to know the pathology and how does it look like. So in YY, it can be asked, you can in SAQ can be asked. Okay, then again, there's another chart here. I will share it later. Okay, that's all for today.